I think we get started with our afternoon session. So first up is Catherine Espiat talking about looking forward with Ulysses and Odysseus and Penelope.
So thank you. And thank you to Julia and the conference organizers for bringing us all together. It's been really great to learn about all the great science that's being done by all the different groups, high mass stars and low mass stars. So I'll be talking about the path forward with Odysseus and Penelope. I'll start off with a bit of review because we are in the third day of the conference and there's been a lot of exciting results that have been presented. And then I'll be spending most of my time talking about work that's in prep and that should be coming out soon, and also a couple of ideas for different paths that we can take to enhance the legacy of Ulysses for the T-Tauri star community. So I wanted to highlight that this is all part of a large collaboration of about 100 experts in T-Tauri stars. And as Nuria mentioned on Monday, this is the first time that this community has come together really with a lot of excitement to work on the Ulysses data set, a once-in-a-career data set. So this is just about, this isn't everyone, they didn't all fit on the slide. And also I didn't have the most recent Penelope team list, but there is significant overlap between the Odysseus and Penelope teams. All right, so I structured my talk into 3 sections to address these 3 questions. So why is Ulysses important for young, low-mass cool stars? So basically a review of the results we've seen so far. And then what is the path forward to wrap up analysis? So in prep work, things that we're working on in both the Odysseus and Penelope collaborations. And then what will be the legacy of Ulysses for T-Tauri stars? All right, so you've been waiting all day for this. So you can't get away without seeing this at least one more time. And Nuria and all the speakers have done a really great job of teaching you what this is, so I don't have to go into detail. But just to recap the main highlights, this is not drawn to scale, but it's drawn to our interest in the community, where we're really interested in what's happening in the innermost disk, the connection between the star and the disk, because of the implications that it has for the evolution of the protoplanetary disk and for planet formation, consequently. All right, and then just because this nomenclature, I'll be bringing it up later on, and I want to refresh your memories. On the left here, we have what we call so this went away. Okay, okay, there it is. See, so this here is this arc here, the arch, that's what we call the accretion flow. That's where the material goes from the disk to the star. And these, when I talk about modeling the optical lines that originate in this accretion flow, I'll be using the models, talking about the models of James Muzzroll, who's here at Space Telescope. And then in the middle here is the accretion shock. So this is right at the stellar surface. And we call this the accretion shock or accretion column. And this is using the models of Nuria Calvet. And I'll be showing this later on, using this model later on when I'm talking about accretion rates that are derived from the NUV excess. And then on the right are predictions for what the hot spot on the stellar surface looks like, where this accretion is impacting the surface of the star. And these are theoretical models from Marina Romanova. All right, so Ulysses dedicated a significant amount of orbits to the high mass stars and low mass stars. About half were dedicated to the T-Tauri stars, and about 100 of those orbits were dedicated to 4 monitoring stars. We've heard a little bit about the 4 monitoring stars in a couple of different talks, but today you're going to be hearing a lot about them, and I'll be presenting those in a few minutes. So you'll be hearing a lot more about the monitoring targets that were part of the T-Tauri star portion of the Ulysses program. And I wanted to thank Ken Sembach for giving the discretionary time for the community to get all this data, Julia for leading the implementation team, all the members of the implementation team, and all the scientists that have come together on both communities to really come and make the most out of this unique data set from HST. And then this is the second and maybe the last time you see this. So soak it in, soak it in. There may not be another talk that shows this for the rest of the conference. And this is just highlighting the goals of Odysseus. So you've heard Odysseus and Penelope, and just to remind you, Odysseus is a collection of scientists that came together, about 100, the T-Tauri Star community, to collaborate and decide what were the main goals that we wanted to extract from the HST data set. And we applied and we got a large archival proposal accepted to fund the research. And then Penelope is a team that got together, many overlapping with Odysseus, to propose, and led by Carlo Manara, who they proposed to get time with the VLT to supplement the Ulysses data set. So we're all connected by Ulysses, but you'll hear Odysseus and Penelope thrown around. So the goals of Odysseus are to measure the accretion flow, look at winds and jets, and also look at the impact of the FE radiation from the star onto the protoplanetary disk. And this is led by Greg Herksig and myself. And one of the strengths of having this collaboration, in addition to getting the funding to make this science happen, was collecting, organizing everyone in the community to try to get as much data as we could contemporaneous with the HST observations. So we've heard a lot about Penelope. So a large program at the VLT getting X-Shooter, UVES, and Espresso data for the Ulysses sample, but there are also some smaller programs, all very important, as you'll see when I talk about the monitoring targets, a lot of optical photometry. So the implementation team got some LCO-GT photometry, but then the community also supplemented it with some additional bands here. And then some smaller observatories, Fred Walter, who's here, coordinated with the AAVSO to get additional photometry. And then here are just some additional optical near-infrared spectroscopy that we got. You see the poster by Fred Walter to see the Chiron data. Will Fisher is here, who led Laertes, getting IRTF spectra. And then also we heard from Christian Schneider about the X-ray component to supplement Ulysses, and also Moritz Gunther has a poster. So a lot of data was obtained by the community through Odysseus to supplement the Ulysses data set. And so far we have 5 publications from the Odysseus team. Most of which is being led by grad students and postdocs, which is very exciting to see HST is still producing PhDs this late in its mission, and particularly in the UV with the UV focus. So that's very exciting to see. And this was the first overview paper that we put out from Odysseus, and we've heard different aspects of the science throughout, and I just wanted to highlight and just show all the data that we were able to get. And this is just one object, and we have this for most of the objects in the sample. We're on the upper right, we're combining in black the HST and X-Shooter data. On the bottom there is the FUV. Here on the lower left is high-resolution optical spectra from the VLT, and then on the upper left we have multiband photometry, and then the black here is tests, because the implementation team worked really hard to try to overlap the HST and already planned test observations. So we also got that great freebie. And then there's also been 5 papers, so it's not a competition, we're all very collaborative. So there's also been 5 papers that's been published by Penelope, and Carlo did a great job with overviewing that, so I won't go over that again. But this is just to highlight Carlo's overview paper of the VLT data set that came out. The X-Shooter here on the left, in red, on the right, high-resolution optical spectra, just to show there was a lot of variability that was seen. And in the middle there, just comparing where the first objects that came out of the sample in Orion, how they compare to previous observations. All right, so that was the overview of what we've done so far and have published. Now I want to talk about what's in prep, so what you'll be seeing in the near future, hopefully in the next 1 to 2 years. So what's the path forward to wrap up analysis? So we heard from Kaylee yesterday about how she's using Nuria Calvet's models to model the HST and UV continuum to extract accretion rates. She's published 1 paper on this and has a current paper in prep, which she told us about the main results of that paper. Preliminary results that the low density accretion column dominates and that less than 10% of the surface is covered by accretion hotspots. So that's some work that Kaylee's is putting together. So that's in prep, and she's going to be covering the entire. She's leading the accretion component for the NUV for Odysseus. And then also yesterday we heard from Adam. So these FUV lines, these hot lines, have been around for 20 years, and Adam is making a very valiant effort in trying to model these very complicated emission lines. And here is just. He actually has 2 papers in prep, one for Orion and then another one for the monitoring sample. So that'll also be coming out soon. And one of the main takeaways that he's finding, as he said yesterday, was that this modeling of these lines, the carbon-4 line is pointing to carbon depletion, which could be an indication of planet formation in the inner disk. Carbon depletion is also seen by Marbali Makolta, who has a poster here, but she's looking at calcium lines from the Penelope data set. So check out her poster. So we're seeing evidence for carbon depletion in different lines. And then on to now, I just wanted to give you some more details about what we have for the 4 monitoring targets, the 4 classical T-Tauri stars that we dedicated 100 orbits to. This is work that's being led by John Wendenborn, who's a PhD student in my group. He unfortunately could not come to the conference because he had an IRTF observing run, which has been clouded out every single night, so he totally could have come. But it didn't work. We didn't know that until it was actually clouded out, so I'll be presenting. These are slides that he sent me, the next 6 or 7 slides or so, presenting his work. So on the left here we have, so the 4 objects are TW Hydra, RY Lupi, BP Tau, and Giamoraigi. On the left we have optical photometry. The different colors correspond to different bands. The vertical lines correspond to the times of the HST observations. So each of the objects was observed by HST for 3 rotation periods, sampling the rotation, each rotation period 4 times, and then separated by a year. So there's 24 observations for each of each of these 4 targets. So we have the optical photometry. Not plotted here is that a lot of these also overlap with tests, and I think that shows up in a future slide. And then on the upper right over there is the HST data for the objects. You can already tell from the continuum there's a lot of variability. That variability is due to variability in the accretion on the surface of the star. And in the lower right are high-resolution optical spectra, mostly Chiron, but also a lot from Penelope, looking at the optical H-alpha line, which traces the accretion flow. And this is separated into 3 papers. The first on the NUV data, which has been submitted, the second on the optical photometry, which has been submitted, and the third, which is in prep and was sent out to the Odysseus calibration for internal refereeing and comments a few days ago. All right, and then just a quick recap for how do we extract accretion rates from the data. So in black are the HST data. On the right there are photometry points covering the optical. And then in blue here is a template star, a weak T-Tauri star, so a T-Tauri star that's not accreting. You see significant excess here. That's telling us that's all coming from accretion. You're going to see this red line move up as I add different components to the model here. So here, this red line is adding the photosphere and then the low density part of the accretion column. So remember, we approximate a density gradient in the accretion column by having 3 separate accretion columns with, here we're going to do, so we have low, medium, and high. Sometimes we have a very high, sometimes we have 4. So if I add in the medium column, you see that the red line goes up. That's the total model. And then here we have the high, and then yes, here for this one we did need a very high. Sometimes we need a very high component when we have a lot of emission here at the shorter end. So we need more high energy, more emission to account for that. So that's just a recap of how we go about fitting the data. And this particular object was Giamoraigi and has an accretion rate of about 10 to negative 9 solar masses per year. All right, so this is the data for the monitoring sample, where the y-axis is accretion rate in units of 10 to negative 8 solar masses per year. On the bottom is the date. We have TW Hydra, RY Lupi, BP Tau, and Giamoraigi going down. So the top of each of the bars is the total accretion rate, and then the different colors correspond to how much of the accretion rate is being contributed to by the different columns, where on the right you have the color code for the low, medium, high, and very high density accretion columns. So what we're seeing is that overall, each of the individual objects varies, and it varies within a factor of 3, which is the typical level of variability that's seen in T-Tauri stars. So we didn't see any significant variability in the sample outside of that. So that's one result. And then another is that there are diverse accretion structures. So for example, RY loop is dominated by the medium column, and BP tau, you can see, has a mix of all the different columns. So it looks like between different objects that the accretion column structure can be different, but it does look to be relatively stable throughout the observations. So it seems that they're relatively long-lived, but they can differ between different objects. So that's an interesting result in John's first submitted paper from this sample. And then something that was somewhat surprising was that when we plotted up, so these are all plots of different line, the accretion luminosity on the y-axis versus a line luminosity in FUV or NUV line luminosity on the x-axis. Because a lot of people have seen, when we look at bigger surveys, that there are strong correlations between the accretion luminosities and the FUV and NUV lines, but we didn't see very strong correlations for the individual, for the monitoring targets, except for the FUV continuum and the NUV continuum, which makes sense because that's where we're measuring the accretion rates from. So what we're taking away from this is that sometimes, and the two particular objects that are screwing with these correlations are TW Hydra and RA loopy, which we heard earlier in the conference, but maybe you don't remember, are face-on targets. So this could be telling us about the geometries and how they can impact what we're measuring. So that's something that we still need to dig into. So these are all the initial papers and results that are going to come out, and then we have to dig in deeper to sort these interesting findings out. All right, so this is from paper 2, which has been submitted for the monitoring targets, and the test data are the cyan. So it's actually pretty hard to see on this scale. Sorry about that, but the test data is there, and the photometry follows it pretty well. So here, what we find, the result that we find here is that the accretion luminosity tracks pretty well with the excess emission that we see in all of the photometric bands. So this was a bit surprising. We were expecting it at the shorter wavelength bands like U and B. We were a bit surprised that we saw it track so well at the longer wavelengths like R and I. So this is telling us that there is still a significant amount of accretion luminosity that's coming out at the longer wavelengths. So it's predominantly coming out in the NUV, but there's still some that's coming out at longer wavelengths in the optical. And then the third paper, which is in PrEP. So here we have for each of the targets going up to down, we have TW Hydra, RY loopy, BP tau, G Miraigi. On the left column is H alpha, middle is H beta, right is H gamma. And most of these are chiron spectra, and you can see the poster by Fred Walter to see more of these close up. And there's about 260 spectra plotted here. So a lot of data was collected for these targets, and you can just see that there's a very wide range of variability that's seen. That, of course, is going to need a lot more follow-up to disentangle all of this. But for our initial results, what John did is he modeled the optical emission lines with James Muzzroll's code, the code of the accretion flow for the material going onto the star. And he extracted accretion rates by measuring each of the lines in the sample. And this is a plot comparing the accretion rates from the accretion shock model versus the accretion rates from the accretion flow model. So again, the accretion shock model is measuring the accretion rate right at the stellar surface. The accretion flow model is measuring the accretion as it's flowing through and before it reaches the stellar surface. So here on the y-axis is accretion rate in units of 10 to the negative 8 solar masses per year. Date is on the bottom. We have TW Hydra, RY loopy, BP tau, and G Miraigi. The different symbols correspond to the different instruments that were used to get the data. And the X's are the HST measurements, the measurements from the NUV continuum, and the colored points are the measurements from the accretion flow models. So they're roughly consistent, but they're not 100%, they're not exactly the same. So that's something that we have to look into, what's happening to the accretion rate so what are we actually tracing when we're looking at the accretion flow versus the accretion shock? But our initial results find that they're consistent, but not exactly the same. So we need to dig more into that. And then I did want to just quickly highlight some of the Penelope work. We heard about this from Carlo, but just to remind you, there's still in prep work, a lot of work that's going to be coming out in the near future from Penelope. On the left, Carlo talked about microjets for one of their next two papers, and on the right they're looking at different line tracers of accretion in the optical near-infrared wavelengths and comparing them to the accretion luminosity. And then some work that's being led by Karina Mauco. So you saw her talk earlier today, but she's leading a program, an ALMA program called Telemachus, to look at the Ulysses targets that haven't been observed in the archive before with ALMA, to give us a better sense of what the structures in these disks that are surrounding these accreting stars, what do they look like, so we can start to make connections. So that should be coming out in the next couple of years. All right, so that's the work that's coming out in the very near future, so in the next 1 to 2 years. And then I just want to spend a few minutes, the rest of the time, talking about what will be the legacy of Ulysses for T-Tauri star. So thinking about what are the different programs that we can be proposing for in the future, kind of along the lines of the discussion section that we had earlier today. So there's still a lot of opportunities for follow-up because we haven't used all of the acronyms. So there are some that are available. So grab your favorite and maybe tomorrow get together and decide what the proposal will be about. But there's lots of opportunities for follow-up. We saw from Nuria Calvet's talk, she highlighted this gap in the Ulysses data set for disks around older stars, and also that this age range is very important. So on the right panel here, that's just showing the disk dissipation time scale. Disks are in the process of being dissipated, especially in that age range where we have a gap in the Ulysses data set. So this gap is there because those objects are just harder to observe. They tend to be in further regions. They tend to be lower accretors, so there's less NUV excess. And of course, we were optimizing the sample to be sure that we were able to get the objects in as few orbits as possible. So in order to make this happen, we would have to put in an HST proposal to look at these fainter objects. We would need a lot more orbits to get that done. Also, we need good template stars, so weak T-Tauri stars that are not accreting. So in the upper panel, what you see is a model photosphere in gray, a weak T-Tauri star observation in red, and a main sequence star in blue. So you see, we have to use a weak T-Tauri star for a template. We can't use synthetic or other types of stars. So we need weak T-Tauri stars in order to accurately get accretion rates. And on the bottom here, what you see is and this is all put together by Kaylee Pittman. This is the spectral type on the bottom. In red are the spectral types for the Ulysses sample, the T-Tauri stars. In red are the objects that have a weak T-Tauri star template that matches their spectral type. And in gray are objects that have no matching weak T-Tauri star template. And of course, the gaps are towards the later spectral types because it's harder to get these objects, especially because they don't have an NUV excess, so you need a lot more orbits to get this. So if this is something that you're interested in collaborating with, Kaylee Pittman is the one to talk to because she's leading this effort to get more weak T-Tauri star templates. And then we heard from Nicole about the importance of irradiation by the FUV, the high energy radiation, the FUV, the X-rays on the disk, and that this has some implications. It should definitely have an impact in the lines that we can see both with ALMA and with JDVST. So you can see here, this is a plot of CN versus accretion rate, and on the top is the FUV luminosity. As the FUV luminosity increases, the CN line luminosity increases with ALMA. And on the right, the orange corresponds to low UV flux, and the blue to high UV flux. And this is water lines, water emissions. So you can see that there should be stark differences, things that we should be able to detect. So with ALMA, the roadblock is there's been a lot of data obtained, so we have to pick the right lines, we have to go in the archive, see which objects have been observed and have been observed, probably have to do a lot of work to show the potential for filling in the gaps in the sample for any that haven't been observed by Ulysses. And then for JDVST, the roadblock is that the T-Tauri star community, we were decimated in the cycle 3 results. We're still healing. Only 2 protoplanetary disks were accepted to be observed. So we need some time to regroup and go for cycle 4 and try to do this again. All right, and then we heard about theoretical work. So Ulysses will have an impact on theoretical work. Once we start putting out more and more of our results and have more numbers, we can start comparing this to theoretical work. So this is just a simulation from Zhao and Ju's talk. And also Uma and James also talked about the importance of the FUV, high energy radiation, and the protoplanetary disk. And what we need to do now is get more results, numbers from the data, and be able to show this to our theorist friends. PDS 70, Justin covered this very well. And then I'll just skip over this, but there are many facilities coming up in the future that we can use. Kevin France is giving a talk tomorrow about habitable worlds, and Connor has a poster on SPECS. So take a look at Connor's poster and also Kevin's talk to really see the big picture view of what the future looks like for T-Tauri stars. And with that, I will conclude. Thank you.
Questions?
Hi. Thank you for such a wonderful talk. On the monitoring targets, when you were looking at the accretion rates from the high-resolution line profiles, I noticed that the error bars were kind of large compared to the variability, but is that because of systematics? I mean, can we trust the actual variability even if we, don't know the accretion weight within a factor of a few?
Yeah, I think we can trust the actual variability because we also see the same, the same factor of variability when we look at the NUV continuum modeling. So it's just a matter that they're offset and we have to figure out exactly why, but the overall magnitude of the variability, I think we can trust that.
Thank you. Very nice talk. I have a concern about matching templates and measuring things, just because if you look at the test data and if you assume all that variability is due to changes in accretion, because it happens pretty fast, you're talking about 10, 20, 30% changes in the continuum level on fairly short time scales. And that's a significant number of spectral types when you're trying to match a standard. So there's a lot more work to be done.
Yeah, there's definitely a lot more work. And thanks for reminding me that I didn't point out that not all of that variability that you saw was accretion variability in the light curves, because it's also due to the rotation period of the star. So the accretion variability is on top of that once you subtract the accretion variability. So thanks for reminding me about that.
You can ask a question if you want. So on the fact that the sort of ratios of the low, medium, and high column doesn't appear to change as a function of time, can that be linked in any way to the knowledge about the topology of the magnetic field, or where the star's field is truncating the disk, right, that it correlates something like that?
Yeah, so that's something that we're currently in active discussions with Jawan about. So we were actually having a conversation about this over the coffee break. So we think that there's some potential there to try to make a connection with the actual theoretical simulations. We just have to sit down and actually look at the numbers and compare. But yeah, that's definitely on our list.
Okay, I think we will thank Catherine again. Talk of the day, we will get down all the way into the brown dwarfs with Tony Panzera's talk on accretion properties of a young brown dwarf.
Yeah, so hi everyone, I'm a second year graduate student working with Chris Johns-Kroll, and today I'm going to be talking about one particular Ulysses target, which is, as you can probably tell, a young brown dwarf. So we've all seen this picture before, so I won't belabor the point, but essentially we're really interested in the T-Tauri phase because this is when the star is actually optically visible. And also we think that planets are probably forming already at this stage. So characterizing kind of the dynamics that is going on is important. Now I couldn't let you guys go to the workshop dinner without seeing this figure one more time. Yay. I appreciate the image. I won't say too much except that accretion is happening. It's truncating the disk and it's facilitating, most importantly, the flow of material from the disk onto the star. You've also all seen this before. So we kind of think of an accretion column. And you can see on the right there, we can see the continuum excess that is indicative of accretion occurring. So just looking at a couple of classical T-Tauri stars, so they are accreting. These are their carbon-4 flux profiles. And as you can see, they're extremely broad and indicative of very fast-moving material at high temperatures. And I want to stress that this carbon-4 is not necessarily produced entirely through accretion activity. There's also a transition region component, as we heard about a few days ago. So a good example of this is our own sun. So the left image is a magnetogram, and the right is at 1600 angstroms. So it captures the carbon-4 line and some continuum. And you can see just naively that the more magnetically active areas correspond to higher emission in the carbon-4. So we really want to try and sort of disentangle what is coming from accretion and what is coming from magnetic activity. So this is a plot adapted from Johns Kroll et al. 2000, and you can see the legend on the left. So basically all of the triangles, the squares, and the diamonds, and the pluses are all non-accreting sources. And then the black filled in circles are the classical T-Tauri stars. And so these are plotted, the carbon-4 is plotted as a function of the dynamo number, well, proportional to the dynamo number. And you can see even as the dynamo number increases, we kind of get a saturation in this carbon-4 flux, whereas in all the non-accreting sources, whereas the accreting sources show a much larger level than we would expect from any kind of transition region activity. So yeah, I want to stress that it's really this excess carbon flux luminosity that is correlated well with accretion rate. And so it's kind of important to define what exactly you're considering to come from accretion and what might be coming from other things. So more recently, accretion onto planets has been proposed, and we've kind of assumed that this is sort of going on in roughly the same way. And so we've gone looking for things that we know to be signatures of stellar accretion. And a good example of this is our favorite planetary system, PDS 70. And so you can see this is a figure in H-alpha from HST wide field camera. And you can see that it is extremely bright in H-alpha, which the authors conclude is possible evidence for accretion. But I think it's important to be careful because we actually don't know whether these relationships, empirical relationships, extend down to these low masses. So they work for, roughly solar mass objects, but we're not really sure what happens when we get down into the brown dwarf and planetary regime. So it kind of makes sense to look at brown dwarfs to try and kind of bridge this gap between what we know about stars and what we want to know about not only low mass stars, but eventually planets. And so, yeah, if you're not familiar, which I'm sure you all a brown dwarf is characterized usually about less than 0.08 solar masses, and it's below the hydrogen burning threshold. Some people call them failed stars. I think that's mean, so I will not. Okay, so I'll be focusing on one specific brown dwarf. It's actually the lowest mass object in the Ulysses sample. So it's 52 Jupiter masses, just less than half a solar radius, 3,000-ish Kelvin. It's an M6, and it's about 100 parsecs away. And I want to note that this is from the Gaia parallax, whereas previous work has just used the distance to the constellation Chameleon, which is like 94 parsecs, so slightly different. And then, as people have mentioned, Tess has been observing these things. So Tess actually observed this object only last year. And so doing an analysis of the light curve, we're able to extract a period of about 1.5 days. So I think firstly, just comparing qualitatively the shape of the carbon-4 line flux profiles to the ones I showed earlier of the accreting objects, I think you can see immediately without doing any kind of calculations that the ones of J0844 are far narrower than those of the accreting sources. In fact, in that Ardilla paper, they actually have some weak-line T-Tauri stars, which have full width half maximums of much closer to J0844, like around 100 kilometers a second, versus the accretors, which are like up to 250. So, but we do know that this star is accreting, for reasons I'll get to in a minute. So it's kind of strange that its carbon-4 flux profiles more closely resemble a weak-line T-Tauri star. So next we wanted to kind of place this star on the plot I showed earlier in terms of how it relates to the dynamo number, and so what we can kind of guess about magnetic activity. And so this is the plot from earlier, where I put J0844 on, and also J1207 from France et al. In 2010. And I mean, you can see that these fall even below the kind of level that we would expect from a magnetically active source. And so, if you sort of look at this plot naively, you might think, well, these two things are not accreting. But we do have evidence for their accretion, both in the optical excess continuum. And so we know they're accreting, but they are showing far less carbon-4 flux than we kind of expect. So that's weird, but I think one thing to note is that in the previous sort of work, as I kind of mentioned before, we were talking about higher mass objects. So I think it's important to figure out what we're actually comparing these guys to when we say they have excess carbon-4 flux. So I went ahead and calculated, well, where these three stars would fit onto the plot. So these are three late M dwarfs. So they're M7, 8, and 9, I believe. VB8 is just a line because I do not know its period, and Tess has not observed it. And then VB10 and LHS 2065. So you can see that these guys show actually a far weaker carbon-4 flux than their like solar mass-ish counterparts. So I think when we then relook at J0844 and J1207, they actually are in excess of what we might expect from a similar spectral type that is a non-accretor. Okay, one more time. So next we wanted to actually calculate an accretion rate to see how this compared. So we did this just using a simple hydrogen slab model, so not complicated models like the ones Kaylee used. So basically we just take a non-accreting template, as Catherine spoke about, and we just added hydrogen slab on top as sort of a proxy for the excess optical continuum that we expect to see. We add those two together and then fit it with some free parameters for the hydrogen slab, like the filling factor, the temperature, the density, and so on. So this has actually been done before by Ruggell et al. 2018. And so what we did is took the exact same, also this is also a cost observation. We took the exact same template spectrum, SO925, fit the slab model, and did the fit kind of exactly as they did. So one thing firstly to point out, which I feel like we've kind of made the point in that these stars are extremely variable. And so you can see that just the continuum level of emission that we see is sort of half as much as what Ruggell found, which is not too surprising because, as I said, these are very variable, but it's still sort of noteworthy that something has definitely changed. And when we calculate a mass accretion rate, we get about a factor of 3 lower than what Ruggell and them found. And I want to stress that I know this is a simpler model than what we've seen before, but the idea was we wanted to compare it directly to what Ruggell did. So we did the exact same templates, the exact same model to get a more direct comparison. With that, I'll conclude. So in summary, T-Tauri stars are magnetically active, can be accreting. Signatures of this are excess carbon-4 emission, but importantly, compared to what? And this young brown dwarf that I showed shows evidence for accretion, both in the optical and carbon-4, but its carbon-4 lines are extremely narrow, like non-accreting sources. So my next steps are to obviously compare these findings to the rest of the Ulysses sample and see what we find. Thank you.
So should we have one over here? Also, I've heard energetic planet is a better way than failed star. So if anyone in the future wants to refer to brown dwarfs as energetic planets.
When you have an object that has a mass that is this low, what's the freefall velocity? I mean, do you actually expect the shock to be hot enough to make carbon-4 and wide enough, like fast enough to make wings that are that wide? Or is that just what you would expect from an accretion shock model anyway? Low mass.
No, so we would actually expect that. So if we kind of assume that the disk truncation radius is about 5 stellar radii, which is kind of roughly what we think it is, and then we calculate the free fall velocity, as if the material is falling from there, we get about 200 kilometers per second free fall velocity, and that corresponds to a temperature of around 1 million degrees, which obviously then, if that is the shock temperature, that's definitely sufficient to heat the pre and post shock gas.
Thank you. So you mentioned, you show us a beautiful picture, plot of the carbon-4, and even though it looks like weak T-Tauri star, there's a slight redshifted in the profile compared to the rest velocity. Can that be used to argue that it's actually coming from accretion?
I mean, I wouldn't say so, because remember these lines are also like influenced by the rotation of the star. So shifts around 0, we can't really say, okay, that means that the material is traveling at a certain rate. That's more the width of the line that sort of characterizes that. So I would say, in my opinion, no.
I would just also add that the COS RV 0 point is uncertain at about the same level as the RV that we get here, so you can't just use that.
Thanks. Active stellar transition regions often show redshifted lines of 10 to 20 kilometers per second because a lot of this emission is formed in a downflow.
So also on this plot, Do you see evidence for a broad component in the same way that we see for T-tauri stars in these lines?
Yes, so I have actually fit these with a double component. Interestingly, so the first component definitely calls for a broad component and a narrow component. It has a much lower chi-square value than just a single. But the second line actually has a better fit with just a single component, which is interesting. So I obviously need to look into that more, but yes, the first line definitely does show a broad component.
That H2 at minus 200?
Most likely, potentially.
The question for those online was if we see H2 at minus 200?
Mhm.
Okay, let's thank Tony and all of our speakers today. I believe now we have the poster pops presentation, so anyone wanting to present their poster, if you can just come on down and line up. Online or in the room? Nope. Okay. Well, there's their poster, so enjoy. Go look at it. Catalina? All right, hello everyone. My name is Catalina Zamora, and I'm a first-year grad student at UMass Amherst. And I'm working on a simulation tool that models scatter in substellar accreting object populations. So we're using this tool to better get a deeper understanding of the scatter in these populations so that we can get a better understanding of our previous observations and improve future observation proposals. So this is which is all in an effort to get tighter constraints on planet and star formation. This is a Monte Carlo simulation tool that begins by assuming an empirical relationship between mass and mass accretion rate. It then propagates error throughout this simulated population and compares it to an observed group, which in this case is the comprehensive archive of substellar and planetary accretion rates created by Sarah Betty. And here are the plots for the tool. So we start off with that empirical relation that I mentioned earlier, and if we could scroll down a little bit. Perfect. We end up at the very bottom down here with the observational uncertainty and intrinsic dispersion propagated throughout the entire plot there. And then moving forward with this project, we're going to implement an initial mass function, because if you can see at the bottom there are little gaps in the masses, so we want to fill in those statistics. We also want to test out the hypothesis that there could possibly be different empirical mass accretion rate relations to see if it will accurately encapsulate our entire observed population. And finally, there is like a population of objects that we see towards the top and the lower mass end that don't seem to get accounted for in our simulation. So we hypothesize that that could be due to different formation mechanisms, and we want to account for that in our simulation. So if you have any questions, please feel free to chat with me later or email me. Thank you for your time. Okay, next we have Suraj.
Hi everyone, I'm Suraj Paudel from Texas Christian University. So in this poster, we are studying the gaseous outflows from the 30 Doradus starburst region. So the 30 Doradus starburst region is a very active star forming region in the LMC, very brightest and probably the most largest star forming region. And we are mainly interested in these like within 1 degree radius from the center of the 30 Doradus. And we use the 8 sight lines using the Ulysses observations for the UV absorption lines. And then we combine this with the radio data for the neutral 21 centimeter neutral hydrogen. And so here we plotted for like various low ions for the UV data as well as for the H1. And we measure the kinematic width of the LMC disk from the H1 data, and this is here. And this absorption here around 0 kilometer per second is from the Milky Way disk. And from 90 kilometer per second to 175 kilometer per second is most often considered as the high velocity cloud. And whatever is remaining in between here to the disk and the HBC is the LMC wind. But since we are looking at the very active star forming region, the like 30 Doradus, we expect very high speed wind and more concentrated wind in that location. Actually, this emission map is from CMPI et al. 2021, where they studied the outflows using the H alpha emission. And they found that in the 30 Doradus quadrant of the LMC, like in the very center, there is the more concentration of the outflows. And there, the outflow speed can reach around 175 kilometers per second with respect to the disk of the LMC. So in this study, we use the low ions, and we studied the trend of the column density as a function of the VLSR. And we found that there is a more stronger absorption at the disk, and if we go kinematically towards the Milky Way, we get smaller and smaller components, getting a minimum at around 100 kilometers per second, and it started rise to again towards the Milky Way. So we find consistency between the S alpha emission and this study and the UV study, that the 30 Doradus region is producing very high speed, like 100 to 150 kilometers per second speed wind, and very concentrated. And there is high concentration at the center of the 30 Doradus, and it's getting down if we go outside. There are other interesting results too. This is poster number 10, and if you have any further questions, we can just discuss later or in the email. Thanks.
Okay, we have 2 more. Find your poster.
Hello, everyone. I'm Suyash Deshmukh. I'm a postbac at Amherst College, working under Professor Kate Follett on adapting quantum Fisher models for accretion column simulations. I don't have the figure from Hartman. Don't worry about it. Gonna start with this corner here. So quantum Fisher models, what do they give us? So they are local line excitation models. You give them a temperature and density, and they output line ratios for line excitation ratios relative to Paschen beta. And they have been used earlier for modeling accretion columns. But the main assumption that was made earlier was, or that was used earlier, was that all of the emission comes from a singular uniform region of uniform temperature and density, which obviously is not the case for real accretion columns. So that's what I want to work on. Obviously, this is complex. So I'm starting off first with isothermal optically thin column, which has variable density in a dipole magnetic system. And so currently trying to figure out how density would change in a real accretion column so that I can use the correct models and combine them in the correct proportions to get more accurate line ratio output. Using the coordinate system from Adamson-Gregory 2012 paper, and using that coordinate system, we can reduce this whole problem down into a 1D problem, which makes stuff a lot simpler. And then using the magnetohydrodynamic equations, can get an equation for density. So these two lower lines are like two examples I had in the paper for how density changes along an accretion column. And so I'm going to use that and hopefully reasonable boundary conditions to then get what the density condition should be for an accretion column, and similar an accretion column with hopefully better line ratios. So that's the current big task, to do that. But why exactly are we doing this is because this wonderful figure, this is from Sarabetti's paper. It has the object Delorme 1AB, and along with that is plotted the Kwon and Fisher models, and in the blue shades, and then in the pink shades is the Aoyama models for planetary shock modeling. So you can see there's some overlap in some of these line ratio plots, but there's a lot of places where they are very separate. And so if we plot an object on these plots, we can get an estimate on like which formation paradigm they followed in their formation process. And so I want to improve this accretion column modeling and then use it on our GWC proposal, where we're observing brown dwarfs in different scenarios, like some isolated, some in planetary mass companions, and see which accretion paradigm they followed. Hopefully, see how the environment can affect a brown dwarf formation, and maybe get a boundary for the accretion paradigms. Yep. Okay. Thank you.
Hi everyone, I'm Marbeli Micolta. I'm a grad student at the University of Michigan working with Nuria Calvet, and my work is based on calculating calcium abundances in T-Tauri stars. And in this work I present you the study of variability, if and how much these calcium abundances are changing. So this is the last time you will see a version of this figure today, I don't know about tomorrow. But again, the T-Tauri stars have the disk, and then at some point they reach the temperatures where dust sublimate and then turns into inner gas disk, and then the magnetospheric magnetic field of the star truncates the disk, and it follows the accretion flows. And in these accretion flows is where the emission lines of the T-Tauri stars form, and they are broad, strong lines we will expect as C37. But then we have cases like T28 where you have the behavior you will expect for the H alpha, meaning that there is that amount of calcium, amount of gas falling in. But when you look at the calcium lines, they're really narrow, weak, essentially chromospheric lines. So for that to happen, and in this case, I'm comparing two stars from the same star-forming region with very similar parameters that should be the most similar cases that we should be able to see. If there is the amount of gas falling in, as we see in H alpha, then there is no calcium in that gas that is falling in, and that we interpret that as a depletion of calcium in the inner regions, meaning that it's been trapped by some mechanism in the outer disk. Our preferred theory is the planet, but there is more ways to trap dust. We calculate the abundances by comparing with the magnetospheric accretion models based on the work from Muserole, that it's from the Space Telescope Science Institute. And we use the ratio between the calcium K line and the H alpha line, and we vary the abundance in the models, and they're shown in the colors. And then the purple color is solar, and then as you go to red, the more depleted it is. I show here some preliminary results of the variability sample that was we were able to do thanks to the Penelope initiative of having observations of these stars. And we see that roughly the overall distribution remains the same. We see a wide range of possible abundances, but there is some cases where the abundance seems to be varying even around outside the big error bars that we're working on reducing. So this is preliminary results. But yeah, we see wide ranges of abundance values. That means that there is some dust trapping mechanism further out in the disk, and maybe it's a planet, some planets as information. We're up to having any discussion of any ideas for this. Thank you.
Is there anybody online or here that did not participate in post-to-pop yet? I don't think so, but I just want to double check. No, then we're good. So in this case, we're going to be wrapping up for today, and I'm not sure how many people are sticking around tomorrow for the Hub Worlds Precursor Science Case Hack Session and the Data Products Office Hours. If you are, I put a message on the Slack channel, but might as well do a show of hands. Who's planning to attend the Hub World session? Okay, and what about Data Products Office Hours? You're welcome to sneak out of the Hub World sessions and go get help with data products. That's also possible. All right, cool. So I think we'll use the auditorium for the Hub World session. And then Joe, Rachel, and maybe Elaine, or at least a couple of you will be in the CafeCon for office hours. If you're stuck on one of the notebooks or you need help using some data products or some of the code infrastructure, they will be here to help. For those attending dinner tonight, there's a shuttle that leaves ST at 5:45. Dinner starts at 6 and it's only a mile ride. I'll probably be driving my car too, so if you need to hitch a ride, you're welcome to, although I'm not coming back here. And with that, I would also like to thank Sharita and Shemaya. Can somebody go grab them outside? If there's a, yeah, thank you. And then Gary, you're alone in there? Thank you, Gary, you were a lifesaver. I know Thomas and others probably were there at some point. So thank you all. Are they coming? Okay. Yeah, Sharita, Shemaya, and our event planning group did a heroic job getting this workshop together. And so I really wanted to thank you very much. It would not be possible without them. And with that, I think we are done for the day. We'll be resuming tomorrow at 9 a.m. for 3 talks. Aida, Kevin France, and Miriam. And then we'll have these hack sessions in parallel. They are 3 hours, but there will be coffee break in the middle at 11. And then I think lunch is going to be served at 1, and then we will disperse, hoping to cross paths again in the future to work on Ulysses or future projects. So anyway, 5:45 for the shuttle for those who are going to the dinner. I think there's about 40 of us. Otherwise, I'll see you tomorrow.